Hey there, guys. We're going to look at example number 3 from our notes. And this one particularly is about a driver seeing a cat and then has to make an emergency stop to avoid hitting the cat. So when you read the problem here, you're going to notice that there's kind of two parts to this. There is this time that's elapsing here, and until she actually hits the brakes to actually slow down. So the time that it's called here is reaction time, and we're going to say that let's see here. Her reaction time is like a half a second, and then she applies the brakes. Okay, so there's this delay time before she hits the brakes. So we actually have to think about this problem kind of in two phases. All right, so let me scroll down here. And the two phases here are, first of all, phase number 1 is the motion while reacting, but the brake is not actually applied yet. Okay, again, there's this time where the car is traveling and it's just going the speed that it was going. Phase 2 is the motion while it's actually braking. So what I'm going to do is I'm going to pause here and I'll come back with you and I will have put together the picture in a little bit more detail. So I'm trying to illustrate here the two different parts of the motion. The first part of the motion is this motion here where she's reacting. She hasn't hit the brakes yet between these two snapshots. So again, this is what I called phase 1. And then there is the second phase of this. This is the part where the car is actually going to slow down and eventually come to stop. And we're going to avoid our little cat here. Actually, I shouldn't say little at all. That's kind of a big cat relative to our car. But the cat here, we're going to try to avoid the cat by stopping the car. So the goal is then to ask ourselves a little bit about the acceleration that's undergoing. So hopefully we understand that because between this one and this snapshot, it's the same exact speed, we are going to know that the acceleration during phase 1 is actually 0 meters per second squared. And as we go between snapshots 2 and snapshots 3, there is going to be an acceleration that's in the leftwards direction here. This acceleration is actually, it does actually say up here. I noticed that it says right up here, it says she's decelerating at 6 meters per second squared. So that's actually here 6.0 meters per second squared. And that's a vector. And of course, that'll be based on our positive direction here. Our positive direction is to the right, so this is actually going to be a negative. So what I'm going to do is I'm going to go down and we're going to summarize what we know in these two phases. So for phase number 1, we don't know this yet. Okay, our initial velocity is, I think it was 28 meters per second. Okay, and that was in a positive direction. Our final velocity in phase 1 is also the positive 28 meters per second. The acceleration for phase 1 is 0 because, again, it's not changing its speed, it's not changing its velocity, and the time at this point is unknown. Likewise, I've listed here all the things I could possibly know. Delta x2 is actually kind of what I'm trying to find. I guess I should put that over here too. I need to find this because ultimately I'm trying to find out how far this car travels. When we pick up with phase 2, the car is still traveling at the 28 meters per second, and we know that it's going to come to rest. So it's going to be traveling at 0 meters per second at the end. It is also going to be decelerating, so that's a negative 6.0 times 10 to the 8th. Sorry, 6.0 times meters per second squared. I'm thinking of the speed of light for some reason. That's 3.0 times 10 to the 8th. And the time, we don't know how long it's going to take for the car to actually come to rest. So what I'd like to do next is think about a strategy that we can employ here to solve this, keeping in mind that the equations that we have for kinematics are only good for constant acceleration. Because we have an acceleration that's one thing in phase 1 and in another one in phase 2, we have to split this up into two problems and then combine the results of these two problems. So here's kind of the strategy I've come up with. Once again, we know that the equations we have are only good for constant acceleration, so we're kind of stuck splitting this into two parts. So phase one is solving for the delta x1 using the fact that it's at a constant speed. The second one, strategy here, is to solve for delta x2 in phase two, and then ultimately to find what I really want, to find the overall delta x. What we're going to do is we're going to actually just combine the two results here. So let me go ahead. I've started doing that over here. To implement my strategy, what I've decided to do here, since there's a constant speed or a constant velocity in this first part, we know that we can use our equation for average velocity, and then if I solve it for delta x1, I'm going to get velocity times time. Putting the numbers in after I substitute and then solve it, I'm going to end up with a positive 14 meters for that. Now, in step number 3, which is where we were going to have to solve for delta x2 in the phase 2, we cannot actually apply this equation. Okay, so again, this equation right here, delta x2 cannot be found by doing this, all right? And hopefully you understand the reason we can't do that. This red flag is because we do have an acceleration, and accelerations, this does not account for acceleration. So we're going to have to find a different equation. So right away, when I see that there's no time that we don't know, I often look at this equation right here, the one that doesn't have time in it. And this is a good candidate because we know that it's stopping. We know that it starts at 28 meters per second. We do have the acceleration, and we want to find the delta x2. Now I like to, at this point in time, I like to cancel out anything that's 0. In this case, the final velocity is 0. So that would leave our equation as being 0 equals the VO squared plus 2a delta x. All right, we're going to end up solving for the delta x2, and I will do that and come back. Okay, so here we are back. I've done some algebra, and I've isolated the delta x2. We are going to bring the VO to the other side so it gets negative, and then, of course, we're going to have to divide by the 2a. When I go over here to substitute in my numbers, one thing to watch out for here, first of all, this minus is not because this is a negative value. The minus is because we had to subtract the thing to the other side. So you're squaring first and then taking the opposite. That's going to get canceled out because we do happen to have a negative acceleration. So in the end, we're going to actually get a positive value, which is in agreement with what we drew in the picture. All right, so when I do the calculation, looks like I'm going to get about 65.3 meters. So to finish up, step 4 said we basically combine these two things together to get our final result. So in step 4, we're going to take the 14 meters, and all we're really worried about here are magnitudes, so I'm not going to worry about the directions here. And we're going to take the 65.3 meters. We add those two things together, and we'll get 79.3 meters for our final result answer. And so this is the answer we're looking for. So as we go back up here to our picture, let me zoom out a little bit. The total distance that the car travels from here during the time that she's has her reaction time all the way to out here where she's stopping, this delta x right here is 79.3 meters. Okay, so we're going to take this a step further. Again, from the four-pronged approach that we have to thinking about situations, we've taken the words, we have made a picture out of that, we have used the equations to be able to understand that, and the only thing left to do to come around full circle here is to do the graphs with that. So what I'm going to do here is I want to think about the situation we dealt with and talk a little bit about what that's actually going to look like as a graph. So again, because there are two phases to the motion, we have this first phase where there's a constant speed, and then there's a phase where there is an acceleration. We need to understand that there's going to be two parts to our graph as well. So we definitely want to make sure when we do our position versus time and velocity versus time that they're clearly showing that there are two parts. Also want to make note that the positive direction is to the right. So these are going to be positive velocities. They're positive displacements. And the only thing that's actually negative here is this acceleration over here. So sometimes I actually think it makes sense to start with the velocity graph first. We know that the velocity at the start is a positive number. And if we remember, positives are at the top of the graph and negatives are at the bottom. It's also constant. So that's going to be this horizontal line. So phase one looks like this. And then what has to happen is we have to have a deceleration, and that's going to look like a straight line. Again, think slope. Okay, slope is equal to acceleration. Notice this is a negative slope. Okay, it's a negative slope, so that means it's a negative acceleration. So this is consistent with our situation. So after I've done my velocity graph, I do want to then think about what my position graph would look like. Since we're moving in a positive direction, that's going to kind of move away here from the zero part of the graph here. It's also constant velocity, so it's going to have a straight line. And then we're slowing down. So kind of continuing from this point, it's going to slow down as a curve and eventually flatten out. And that would be what our graphs look like that describe the very same situation that we've just solved.